We are going to start this session. We are going to start with the introductions. My name is David Garcia, or David. I'm a software engineer working at Canonical, and I've been involved in the OSM project for more than 1 year now. And
I'm Dominic Fleshman. I'm also a software engineer. I will be supporting David in this presentation if you have any questions. I've also been now a year involved in OSM.
Hello, my name is Dmitrii. I am a software engineer at Canonical working on the operator framework, and I'll be talking about that during this presentation.
Okay, today's session is about the introduction to VNF operations. This is the real important thing, the long-term operations, because deploying workloads is okay, but what we need is we need to operate our workloads. That's what will bring us the economic benefit, and we should start with the next slide. And when we have OSM, we deploy our workloads, but we need some place, we need to know how to operate these workloads.
Sorry, David, I just want to make one point. Key thing here is the idea that OSM is a standalone application. It's a general application. You don't want to have to change the code of OSM. You don't want to hard code into OSM the details of any particular workloads. And similarly, the workloads might often be fixed, unmodifiable, right? That workload could be a PNF, it's an appliance, you can't modify it, or it might be a VM image that you're not allowed to modify, or it might be a Docker image that you're not allowed to modify. So we need a third space, right? We need a container, could be a virtual machine, could be a container. We need a space to run code that is specific to that workload, the operations code for that workload, the sort of operator instance effectively of that workload. And the code for those operations that is embedded inside the VNF descriptor, the VNFD.
Yeah, that's right. And what OSM will do is basically talk to this piece of code, and that piece of code will actually operate and do actions to the workload that we have. So now we will go a bit deeper into the VNFD. And the VNFD basically has two parts. The first part is the metadata, that is basically declarative data in which we specify how many BDUs do we want in that VNF, how many interfaces do we need for each one of those BDUs, and we specify all of that in the metadata. But then we need that operations package that we were talking about, and that operations package is called a charm. That charm manages the life cycle, the configuration, operation, and integration of our workloads. We'll start with the life cycle. With life cycle, we mean installing, for example, a workload, installing some packages, some dependencies, and so on. We also need to know, we also manage the scale out of the application. So, for instance, we could have one instance of a workload, but then we may want to scale that to 3. Also, the upgrade of the workloads, upgrade of packages, and so on, and report the status. Those are some of the lifecycle operations that we can manage with the charms. Also, we can do some configuration specific to each of the workloads. there's the initial configuration that is basically some configuration that we pass it to the charm when we deploy, but afterwards we can also modify and change that configuration, and the charm can handle events so that configuration is correctly applied. And basically, the configuration is a YAML file inside of the charm, in which you specify the options you have and the type of those options, and you just you can put any values you like, and then manage that in the code. Okay, now this is the best part of the charms, and it's basically that we can do operations, for example, backing up, monitoring, debugging. We also can add users, policies, rules, manage certificates, and many things. But the important thing here is that we can do custom operations. So the user, the developer, is free to add whatever action he wants to the workload. So there's no limitation on the number of operations that a workload can support.
So I think it's important to say that it's not the end user that is adding these operations. All of these operations are pre-packaged in the charm inside the VNFD. And since that is typically open source, across a community of users effectively, you can grow a rich set of operations primitives for each widely used workload.
Yeah. And it's important to make this point, and is that each operations primitive is a function call that basically takes parameters and produces a result. Then we also manage with the charms the integration between workloads. We have relations to integrate one workloads with another. So we can also, if we want, we can add a new workload into the existing topology that we have of workloads and integrate that workload with another workloads using relations. Okay, so as we show in the first slide, we have OSM and the workload, and there's this third part that is the operator code, the charm, which manages the actions and the operations to the workload. So sometimes the workload and sometimes the workload can be modified, and sometimes it cannot be modified. So when the workload can be modified, this third part, the operator code or the charm, can be in the same machine as the workload code. So basically, you will have the operator code into the workload code in the same machine.
So let me just say this differently. Imagine your workload code is an app that you can install. So it's an app on CentOS, or it's an app on Windows, or it's an app on Ubuntu. Then you can imagine that you can create a clean machine, and you can install the app, the workload code, and you can install the operator code, the charm, in that same machine. That's very much like having an application and Ansible on the same machine to modify the configuration of the application. Right? In that case, you have what we call a native charm. Sometimes, however, the workload comes as a fixed machine definition. It comes as a fixed and unmodifiable physical appliance, or it comes as a fixed and unmodifiable Docker image or VM image. And then you need to have two separate machines. So if you have two separate machines, then we call the charm a proxy charm, because it is at some distance from the actual workload. It's talking to the workload over the network. The code is exactly the same. The delivery mechanism is exactly the same. It's just that when the charm is distant from the workload, then it can only operate on the workload over the network. So in the case of a proxy charm, your execution is typically calling netconf-yang or calling XML-RPC or calling remote procedures on the workload, whereas when you have a native charm, your charm is installed inside the same machine as the workload, on the same file system as the workload, and it can operate on the configuration files of the workload directly.
So now I will show a basic demo of one action. Okay, this is my OSM UI, in which I have deployed the reverse proxy network service. I have the instance here, okay, and I can, let me make this bigger, and I can show the history of operations, the list of actions that the charm has done into the workload, okay, and basically what, well, let me go to here. Okay. So we are going to search for the VNF IP that is basically here, okay, and currently the workload is configured, the reverse proxy is configured to target the OSM wiki. So as we can see, if we type the IP address of the workload, we can see the OSM documentation. So now we are going to execute one action in the instance, okay? And basically here what we have to put is the name of the primitive, the name of the action, that is set reverse proxy. Then we specify the VNF member index that, as you already know from other sessions, this goes into the VNF descriptor. And then here we can put the primitive parameters. Okay, so the first parameter is location, and I will put that in the slash. And then we put the target. And we are going to put here, for example, the OSM K8s website. Okay. So we can execute the action. Go to the history of operations, and the action has been finished. So now we could basically go to the same IP. Okay. Okay. Maybe this is the cache. Okay, to the private window. And basically, we see clearly that the workload has changed its configuration by executing an action through OSM. It's just a basic demo of one simple use case of a workload and how we should operate the workloads through OSM. It's really simple, really straightforward. So let's go back to the presentation. Okay, I will imagine there are no questions. So now we are going to explain the Kubernetes operators that are basically charms. So in the Kubernetes world, we have the workload containers, and here we will face the same problem as in machines. We have workloads which basically usually are not, we cannot change them because they come in a Docker image. So we face the same problem. We need a third thing, a separate place in which we should put the code to operate the workloads. This other pod, or this other container, is the operator pod.
people who invent Kubernetes clearly haven't spent a lot of time in telco, because they would never have chosen to call a container an operator if they were going to go to a lot of conferences full of operators. It's going to be a bit confusing, but when you see the term operator in the Kubernetes context, it really just means a container that has software in it to drive the other containers. So in the OSM context, the charm is put into a separate container, and that container in Kubernetes language is called an operator container. Right?
Yeah. Okay, so to make a summary of the charms are part of the VNFD, the VNF descriptor, and they can manage lifecycle, configuration, operations, and integration. We also have the ability to write charms for both operating machines and Kubernetes workloads. So this gives us a very huge advantage, because learning once how to code the charms, we can target easily legacy machines and Kubernetes workloads and make a clean transition from one to the other. And also, charms are basically code. So I will introduce now my colleague Dmitrii, that will explain basically how this code looks like, and it will show you the basics to know how to code the charm.
Hello, this is Dmitrii. I'm a software engineer working on the operator framework, and I represent the team at Canonical that does that. Our initial goal with the operator framework was to make it easy to write Kubernetes operators in pure Python, but we didn't stop there. So we have this code base for both legacy workloads and for Kubernetes workloads. Today, Operator Framework is a Python project. It's open source. It's available on GitHub. It has a class hierarchy for modeling your services and their integrations. The idea here is that a charm author wouldn't need to think about creating his own abstractions for working with a Juju model, and will provide them with the right types and abstractions which are tested and which make sense based on our experience after operating a lot of applications. This framework also has an event system that helps you to model the lifecycle of your application. There are also a couple of other things, such as the persistence layer, which enables us to store data between individual hook executions, and to allow for capabilities such as deferring events. The project has minimal dependencies. Depends on Python 3.5 and its standard library, and a PyYAML library. So why did we choose Python? Python is a high-level programming language that is widely known. It has a relatively low entry barrier. Our experience shows that it's good for writing the integration code. And when it comes to debugging, you can easily do that in place, which is a useful feature when you're working on deployment or in production when something goes wrong. It's much easier than pulling in debug symbols and actually looking at the interpreter code instead. It also works wherever your Python interpreter works. So regardless of the architecture, you can execute your Python code without additional modifications. So that's why we chose Python. As I said before, our goal is to make sure that you use the same approach with legacy workloads and Kubernetes. So charms written in the operator framework can target the machines with different providers. So you could have OpenStack, bare metal, or public cloud providers use with those charms. And you could also have charms on Kubernetes talking to each other using user relations. And this kind of approach allows for reuse of code and the existing modules. We've also introduced the event-driven programming model into writing charms. So your charm code would look something like this. You would have your charm type with the events that you would like to observe declared, and there would be handlers that would handle those individual events. For example,
so just to be clear, the charm to handle your workload is a class, which can inherit from the charm base class, and by inheriting from that class, it's essentially gaining all of the standard primitives that it's going to need. And that charm essentially, that instance of that charm, which is running on the VM where the workload is, or one of the VMs where the workload is, it's managing the software only on that VM. So if you have a sharded application, a database that's spread across 5 machines, then the charm is on each of those 5 machines, and the instance of the charm is only looking after the piece of the application that's on that machine. The framework will deliver to that instance a stream of events, and your init class, your init method effectively, is where you say which of those events you actually are going to handle. And each event handler is just a method on the charm object, on the charm instance.
So as you can see here, the install method of your charm handles the package installation, and config changed handler would react to a change in config and re-render the template and say restart the service. So that
in each case, you will know what has to happen there. So for example, the install method might go and get a Windows package or a CentOS package, or in Kubernetes, it might launch a workload container. A config changed method in Linux might rewrite a configuration file and restart the application. In Kubernetes, it might ask Kubernetes to restart all the containers with a different set of environment variables.
So when it comes to generating events, there are different kinds of events that you might have in a large model. For example, there can be changes in the graph itself. So you might have a single unit of an application at first, but then as additional units are added, you need to handle those additions and thus make changes to your workload. For example, a load balancer would react to backends added for a web application. There are also changes such as config, which come from an administrator. So this is something that can only be initiated by a human admin. As an output of that, you want to provide an operator a view of your model and the current states of all the charms. So on the picture here, you can see that one application has 3 units and another application has 1 unit, but they all observe each other. And the events that you'll see is that you have the first application deployed, then the second one, they're related to each other. And the 2 initial units first observe each other. And as we add units to the model, the unit of the application B starts observing more units of the application.
So I think the important thing here is to understand that a large topology of VNFs is a complex thing, but each individual step required to get to that large topology is a simple thing. So often we will put up on a whiteboard, we will put up a picture, you know, with 15 different VNFs and lines of integration between them, and highly available, you know, redundancy, fallbacks, and all of things like that. What we do is we decompose the construction of that complicated graph into a stream of events. And the charm deals with those events one at a time. As far as possible, you want to encapsulate everything required to deal with a single event inside the handler for that single event. And then the behavior of the entire cluster is an emergent property rather than a designed property. So the build-up of that complicated picture of having a single instance application talking to a scaled-out application doesn't happen at once. You have an event when the first instance of the scaled-out application is deployed. You have another event when the first instance of app B is deployed. And then you have a stream of events as further instances are deployed and become aware of each other.
One related idea is that you need to be able to execute a certain portion of code locally close to the target workload and be able to handle events that are relevant for you. So you can think about all events in a distributed system, but it won't be very effective. And you need to only think about a slice of that. For example, you could watch.
Let me put this differently. This picture looks like a holistic picture, right? We look at that picture and we understand intuitively the idea that we have all of these different pieces of software. But remember that each individual piece of software is running on a separate machine. And the software that you write is going to be installed on one of those machines or a few of those machines. And so that software doesn't see things that are happening far away from it. That software will only ever deal with things that touch that specific machine. So that's what we think, that's what we call the event horizon. Your piece of software will only see events that are directly connected to it, right? This central workload, if that was a VM running a VNF and your charm was there, it will only see events from the workloads around it related to the specific integration with itself. It won't see any events further away in the graph. And so that is really important in terms of simplifying the experience of the developer, because they by definition, they write code which is reusable, right? That this workload could be in many different graphs. It is unaware of everything else that's happening in the graph. It's only aware of the things directly connected to it.
Now we'll switch over to the description of how to write a charm.
I think you should just take questions at this point, because those are all the concepts. That's the overview.
Yes, I have a question. I'm Antonio Romeo from Radcom. Hello? Can you hear me?
Yes, one moment. Someone is making a question.
Okay, we can't hear it then.
Can you check your laptop? Can you repeat the question, please?
He hasn't asked the question yet.
Hello?
Yeah, I don't know if the presenters can hear you. Just hang on.
I think the person asking the question is...
So if we can't hear people, then we need to stop. We need to get to the questions.
But what is the order? Okay.
So maybe ask a question, I'll transcribe it into our internal chat. Or transcribe the question on the side.
Yeah, okay, I don't
So
know
we
if,
just realized that we can't hear you at all. So we need to get our audio right so that we can take your questions. Can we, what was the audio?
Maybe to save some time, could you ask the question and then
We need, sorry folks, we just need you to understand that we can't hear you right now, so we need to fix our audio. If someone else on the call could speak, then we will know when we can hear you.
yeah, so can you hear me, Mark?
Right, can you speak, please?
Actually, the voice is recording.
There we go. Now we can hear you. Thank you very much. And I just want to confirm that you can hear us.
Yes.
Great. All right. Thank you. We'll continue. Were there any questions? And my apologies, we didn't realize that we couldn't hear you. Was there a question at this stage?
yes, can you hear me?
Yes.
Yes, we can hear you now. Go ahead.
Okay, yes. I have a question regarding the events. I mean, the events, when you said that the machine A observed the machine B, I mean, I'm thinking, for example, in the deploying P gateways in the edge, right? So the central system is to see if there is more, let's say, traffic in the edge, in the P gateway. So they need to scale out the NF or the VNF, right? So these events also includes monitoring events. I mean, like increase on load or something like that. So then you can decide the charm.
Let me kind of provide some clarity on the architecture of OSM. So the VCA, it's not the job of the VCA to make policy decisions about what should happen. It's the job of the VCA to implement decisions about what should happen. So in the scenario that you're describing, the monitoring pieces of OSM would observe the load and would take a decision about scaling, right? Because that's a business decision. That's an allocation of resources decision. That monitoring element would essentially say, okay, we're going to allocate more resources to this function. It would talk to the RO in OSM, the resource orchestrator, which would go and get another VM, which is essentially buying more compute to solve this problem. So that's a resource allocation problem. And it would feed that VM to the VCA, right? And so the VCA's job is now to get that VM to do the work, right? The policy decision that we need more capacity to do this work, that was taken somewhere else. The VCA is reacting to that policy decision, and it now needs to take this resource, this new VM, and make it work, right? It needs to essentially make sure that the right software is there and configured correctly, and equally importantly, it needs to make sure that all of the other VMs know that that new VM is there. Does that make sense?
Yeah, makes sense. But then it's not the responsibility of CHAM. When you make a CHAM workflow, it's not for this purpose, right? It's just for configuration.
You are right. You are essentially in the CHAM. What you're defining is how to handle policy decisions, right? If the policy engine says there should be another 5 database units, then the CHAM's job is to make sure that those 5 database units work and that all of the applications can talk to those 5 database units, right? The CHAM's job is not to decide that there should be 5. And the reason for that is it's the separation of operational logic from business logic. So, you know, one operator may say, look, we're a low-cost operator. We're going to run those units very, very flat out. So we're only going to put 3 more database units there, right? A different operator might say, look, we're a premium operator. This is our best customer. We'll put 6 units there. The charm should be the same charm, right? Because you want reuse of the operational logic between all the operators. Again, operators in the telco sense, right? So the charm essentially doesn't encode policy. That's handled somewhere else in OSM or in OSS/BSS, right? The charm says, okay, if you want 6, I'll give you 6 that work, or if you want 3, I'll give you 3 that work, and I'll make sure that all of the other VNFs know about the 3 or know about the 6. So the events that we're talking about are essentially just changes that the individual piece of software needs to respond to because a policy decision got made. Does that make sense?
Yeah, very clear. Thank you.
I just want to say one other thing. Sometimes that policy decision might be told to the VCA, and the VCA has to go do the work. Sometimes, with auto-scaling in particular, you can imagine it might happen the other way around. Sometimes, for example, you set up an auto-scaling group in Kubernetes or in a cloud, and so the cloud, the infrastructure decides, however it decides, it's going to decide, okay, I need another one of these. And so the event gets triggered a different way. The event gets triggered from the bottom up. But again, it's not the VCA that's triggering that event, right? If the cloud decides to spin up a second VM, then the VCA will notice that and say, okay, now I need to go and tell all of the existing database units that there's another database unit. And I need to go and tell all of the existing application units and logging units that there's another database unit, right? But in neither case is the VCA, Juju, making the decision to scale.
Mm-hmm.
Okay. Any other questions at this stage? Okay, should we dive into the code?
All right. So in order to start writing a charm, you need to understand that there are different parts of a charm. So there is a declarative part and something that you actually need to implement. So the metadata and config represent the declarative parts. And your charm code
It's just Python.
It's just Python. In order to start with the charm implementation, you need to declare your charm type and tell the framework to actually use that type. So that happens when you pass the type into the main function of the framework. All charms inherit from the charm provided by the framework called charm base. And the directory structure is familiar to those who have written the charms before. So you have your source code under src charm, and you have your modules under it. There can be different ways for a charm to affect the workload. So the traditional one is that you have the charm located close to the workload on the target machine. And you would observe an install event coming from Dmitrii and handle that in the onInstall handler. You'll notice that every handler has an event passed in. So for more versatile events rather than install, you will get additional attributes on that event object that will help you to work with the model. In this case, it's fairly simple, so you just get the packages from config and install them, and that happens on the target machine directly. When it comes to naming your charm type, you can use any. You just have to pass it to the main methods of your framework.
Any questions so far?
The other approach is when you have charms driving the state in Kubernetes. So the difference here is that you don't need to affect the target workload directly. You need to specify an image to be used for the workload and additional configuration for it. So you don't do that by running your charm code in the workload pod. Rather, you tell Kubernetes that you need a deployment with these parameters, with this image, this amount of pods, and so on. And the charm effectively becomes a driver for the desired state in Kubernetes.
Kubernetes doesn't let you mess with the workloads. It only lets you tell Kubernetes roughly how you want the system to look, and then Kubernetes will go and make that happen. So this install handler is essentially just saying, hey, Kubernetes, here is the spec I want. Here is the desired state that I want. I want these pods running. And that's what that set spec method call in the framework does.
You'll notice that you can access things by referencing yourself, and yourself in this case is the charm object. And every object in the framework allows you to access the model, for example. And the model gives you useful types and primitives to access the context that you have. So in this case, you can set a spec for your Kubernetes deployment, but there are other examples which I'll show in the following slides. One very useful ability that Juju gives you is handling multiplicity of your workloads. So you have an application, but there are units in that application. And in this example, you have a web workload that you want to scale out. And there are 2 units of a load balancer. Well, load balancer units need to react to changes in the number of backends so that they can spread the traffic across multiple workloads on the backend. So if you think about your load balancer charm, it would have high-level events such as the addition of a backend, and you'd want to handle those. You can see a handler for the backend relation joined event, and you want to obtain an address of the workload that just joined the relation. You can use the event type to access the relation that's associated with that event. So you do event.relation, and then you access the data by accessing the data attribute. And you can pass a unit associated with that event as a key to retrieve a relation data for that specific remote unit, which is Web1 in this case. And then you can obtain an address of that unit and emit a charm level event called backend added, and pass in an address to say that, oh, this is the exact address that that was added and that you need to modify your configuration for. So relation data, there are different kinds of relation data. There is unit relation data and the application relation data. You can think of it in terms of a scoreboard. So you have individual players that have their individual scores, and there is a team score as well. Relation data is somewhat similar to that. Your applications have leader units, and those leader units can say, well, this is the data that I want to expose on that relation from the perspective of my team. So a leader unit will be able to say rights to relation data of application A. and individual units would be able to write into their own relation data buckets. So just to go into more detail on this, a unit called database 0 would be able to write into its own data bucket shown in red, and then every client on the other side would receive a notification about that. So this allows you to sort of broadcast the changes in relation data to remote units, and thus change the target model according to your needs. For example, a database could expose an IP address to be used for connections or credentials that are needed for that. There is also a different kind of topology change, which is change in configuration. So an admin can modify the configuration for a given application, and in order to access the config, you would use the model provided by the framework. So in this case, you have a load balancer application, and it has a request timeout config. What you want to do is to obtain that config and use it in your template. So you form a context using some templating such as Ginger2, and you pass in that resulting context. But the mechanism of getting there is the same. You observe a config changed event, and you handle it in the on-config change template. And then every unit of a load balancer reacts to that config change event. In order for you to define your own events at the term level, you need to declare them. So if you wanted to, say, declare a load balancer started event, you would use the event base type as the base type provided by the framework, and then you would also declare a helper type that would group events for a particular charm, and this is what's represented here as the LB charm events type. You would also need to use the onT helper, and you pass in an instance of the LB charm events to that. And for example, after you install the load balancer service and started it on your target system, you could emit the LB started event from your charm perspective. That would also have its own handler, but you'll notice that this event doesn't come from Juju itself, it comes from your charm. So if you need an analogy, you could think about a GUI application which has an on-mouse clicked event and on-button pressed event. On-start would be on-mouse click, and LB started would be on-button pressed.
This is important when you start thinking about your charm interacting with other charms. So your application wants to talk to a database. Your application wants to talk to an FCAP system. Your application wants to talk to a log analysis system. Your application wants to talk to an intrusion detection system. Since those other systems come from other vendors, they will have written the charms for their software. And to make your life easy, what you need to see is that you can import their Python code and deal with events that they emit in a very clean way. So your experience of integrating with that database becomes as simple as loading a Python module from that vendor and then dealing with some well-documented events that their objects emit. And so the integration, the process of integrating workloads from different vendors becomes much cleaner because it's all pure Python and it's just events and it's just objects.
There are also different kinds of events called actions. Actions are one-time events triggered by administrators. And this is different from the lifecycle events which I was describing before.
This is actually the kind of event that you would see exposed in OSM as an operations primitive, right? Back up the database. So the trigger for this event is simplistically a human administrator doing something, right? In OSM, in the OSM GUI, that's called an operations primitive. Under the hood, that is mapped to a Juju action in the charm, right? And it is effectively in the charm, it's delivered as an action event to the charm. And the event handler for that event, that action event in your charm, is where the operations logic to back up the database or to add a user goes. Right? The trigger for that event, though, is an external agent. It could be an OSM rule, or it could be an OSM human administrator, but it's not the system itself.
In the previous demo I showed about the reverse proxy, I went to the UI and there I specified the name of the primitive, which was set reverse proxy. So that has in the charms code has a set reverse proxy action. So that function is the one that handles the action that it's invoked in OSM.
Here you'll notice that we not just exposed a feature and provided some hook tools for you to work with. We've also modeled this from the object-oriented perspective. So an action event has a useful API and methods to work with things that you can do with the action. So you can request its parameters, you can log the progress messages, which will be output to an operator as the action executes, and you can set the results of that action. One thing about actions is that they cannot be deferred, so it doesn't make sense to defer a one-time action that has a certain context. So if your execution finishes, then you shouldn't have the same action re-triggered on the next one. So that's one detail about actions.
So in the action event handler must produce a result effectively, right? Even if that result is, I can't run now, an error, effectively it has to be dealt with immediately.
So just to give an example of how what I've described so far can be used for a stateful workload, if you have a database that you need to run in a highly available mode, you need to bootstrap it somehow. What you start with is initializing a cluster and generating a new cluster ID. That's fairly typical for different kinds of database applications. And Juju provides you the means to synchronize this bootstrapping process. So every application has a leader unit, which can also act as an initial unit when bootstrapping a cluster. And there is a concept of a peer relation where units of a given application observe each other and can exchange relation data. There's also a concept of application relation data, which is applied to peer relations. So a leader would be able to expose some data on the peer application relation data back. And that could be a cluster ID that I just mentioned. So in your install event handler and your config change event handlers, you could have a code to set up your database and start your cluster. And then you could emit a cluster initialized event at the level of that chunk. You could check that if you're a leader, then you can write that cluster ID into the application relation data. In order to do that, you obtain a relation object, which you can see here. It's named the cluster relation. And then you would need to get to the dictionary called cluster application data. For that, you would access the relations data and pass in the application for which you want to write some data. And then you would write, let's say, a unit name and the cluster ID into the peer application relation data. And every other unit, every other peer would see that cluster ID and be able to use the connection details to the initial unit to form a cluster. So this example is an extension to that. So it's not about peer relations anymore. You can have application relation data for non-peer relations. And it works in the same way, only your remote units are units of a different application. So a leader on one side writes some data to the application relation data bug, and every other unit on the other side would receive that data.
Can we just stop there and take questions on relation data? Did we put up that picture yet?
Yep.
Where is it?
It's a little earlier.
Maybe one more. This one. So this is a really important concept in thinking about how parts of the system communicate with each other, right? So if you've got an app talking to a database, then simplistically the database might say to the app, here is my server certificate, here is my port and IP address. You know, here are some macro level things that you need to know in order to have an effective integration with me. And that expression is at two levels. One is at the macro level of the whole application, right? So for example, if that database is spread across 5 machines and they're all going to use the same port, then you just have one piece of data at the application level, the application app A data, which say port 8449, right? And then you'd say, okay, I'm going to use that port for every instance of the database, right? Every unit of the database. But individual units, if you spread across your database across 5 machines, you've got a big Mongo cluster, then each individual unit may have some specific data that it needs to express about itself. For example, it may have its own separate certificate, in which case then it would express that in app, A/0 data, right? So then that's expressing data that it's specific to the specific slice of the database, right? The VDU of the VNF. Are there any questions about that? Okay. Is somebody asking a question? We can't hear. How did we lose audio again?
No, I think it's in the other room. Somebody was talking in the other room.
Could somebody ask a question just so we know we can hear you?
Hi.
Okay, all right, we can hear you.
Okay.
All right, so is everybody comfortable with relation data? Okay, so
Yeah.
the events.
Sorry.
Sorry, say.
I want to ask how we can pass the parameters between the applications. If we need to get another application parameter which is decided during the launch, for example, is IP address. We didn't give it certain IP address. Maybe it is assigned by the OpenStack. Then after all the VNF launch, we need to get their some specific parameters in real time. So is it possible to use relational data between the VNFs?
That's exactly right. That's exactly how you should do it. So if you think about it, each unit of the application knows its own IP address, right? And so it can communicate that over this relation data bus, if you want to think of it that way, right?
Yes.
The way this works, that line between application A and application B, that connection, that integration can only be created if the charm for A and the charm for B both agree that they can speak the same language, right? So in other words, I can only integrate A and B if the charm for A says, I speak a certain charm interface, and the charm for B says, I speak the same interface. So that's how we know that the charm A and the charm B have the same expectations about what's going to be in this data bag, right? Because they've declared that they speak the same interface, we assume that that means that they essentially have read each other's documentation. And so they know that part of the conversation between them is going to involve, for example, sharing IP addresses. If they don't need to share IP addresses, then the documentation wouldn't say there's going to be IP addresses there. If they do need to share IP addresses, then the documentation would say, okay, app B is going to present its IP addresses for each unit, and it's going to be here in the data. The data blob for each of these things is YAML. So app A data is a YAML document. A0 data is also a YAML document. A1 data is also a YAML document, right? And the structure of that data is essentially up to the charm authors, but you can imagine that since both A and B have said, okay, I speak this interface, it sort of means that you can assume that they have the same expectations about what A and B are going to write into their data bags and when they're going to write it, right? So for example, the handshaking across that interface might be, first we will tell everybody our IP addresses and our certificates, and then after they've established secure connections, we will then put more data into the data bag. All of that understanding effectively comes from the fact that both charms have said that they speak the same charm interface, right? The important thing to remember in practice is that only one developer, one vendor typically will create that interface, or specify that interface, and what they will actually do is they'll implement in Python both the server portion of that interface and the client portion of that interface as a Python module. And so if you, for example, are writing the charm for A, and this interface was specified by B, right? So say B is like the database, Postgres. Then what you do in your charm is you just import the library from B, right? That has a class in it, which essentially was written by the author of charm B, right? So you as charm A, you're just importing a library, and then inside that library, it will handle all of the handshaking, right, between A and B for this interface. And all you will get in your Python in A is you will get the events, right? So you know, we're showing you what's going on underneath the hood, but what this comes back to is that you've just imported the database charm objects effectively, and their documentation says, okay, there's one event, which is when the database gets connected, and all you do is you say, okay, I'm going to handle the event when the database gets connected. All of the actual work will be done by that library that came from the author of the charm for B. Does that make sense?
Yeah, actually, the interface is the answer of my question. I know it, but I couldn't find more example how to do it. I tried some interface to implement, but it's not successful actually. If there are more examples about interfaces to talk applications, more applications to pass parameters, server and client model, it will be very useful. If it is possible, could you please share some interface implementations within the VNF?
Yes, we're going to walk through some charts a little bit during the hands-on session. Do we have an handler in that code?
Yeah.
Okay, there is an interface example there. And then what we can do is we can run a regular office hours, a regular WebEx or GoToMeeting or Google Hangout, where we can go through your charm code with you and help you with problems like that. Does that make sense?
Yeah, thank you. Thank you.
We can do that once a week in a couple of different time zones. And then anybody who has a charm issue can hop on and we will help you with your charms. Okay?
Okay, thank you.
So just to summarize, relations help you to connect otherwise independent applications together and get a fully integrated model working. I'm just going to go back to the slide that I stopped on. But just a summary of application relation data. You can write to it if you are a leader unit, and everybody on the other side will see the change. Here, application relation data effectively access data of a leader unit for a particular application. And you can access that using the model object provided by the operator framework. As you can see here, you get a relation, get to the data of a particular application, and you either get or set a specific value. We also introduced the concept of a stored state. This is to help you with modeling the lifecycle of your application based on some data that you persist between hook executions. So, for example, if you wanted to store a variable that would tell you if you started a service or not, you could set that variable as an attribute on the stored state object, and it will be automatically persisted and restored in between the hook executions. If you wanted to set a default value, you could use it. You could use the set default method and provide a specific attribute that you want to set to a certain value. So if you think about the sequence of events, first you have the install event. Since you set it, the default value to false, the initial state will be overridden. There's no state initially, so you write started equals false to that. And then the install hook execution ends, and your Python process dies. And then on the next hook execution, a new process is created, and you need to handle the start event. Well, after you start your load balancer service, we can set this variable to true, and this will automatically be persisted by the framework when you exit from the start event execution. And then when the config change event happens after that, you will be able to access this stored value, and it's completely transparent to you how exactly that happens. What you need to worry about is just accessing the right variables at the right time, and you don't need to worry about saving this value into some file in a completely child-specific way. So this is a standard mechanism of storing state across the executions.
Yeah, so I want to just spend a little bit more time on this. Because this is an event-driven system, and because it's a distributed system, it's impossible to know what sequence the events are going to come in, right? The database might get connected to the application before the logging system gets connected to the application, or the database might get connected to the system after the logging application gets connected to the system, right? In distributed systems, there are often race conditions and things like that. So that's why the idea of this being a pure event system is really important. Also, you don't necessarily have persistence. So it's not like your charm starts running and then stays running and sees all of those events. Your charm will come up and deal with an event, and then it'll go away. And in a Kubernetes world, it might really go away, right? That container might get shot, disappeared, killed, removed, deleted, and 5 minutes later, a new container gets instantiated on a completely different host. So this persistence piece is really important. You deal with the events. If there is something that you now need to remember, you persist that, and then you can go away. The next time you get instantiated, even if you are effectively in another universe, another container on another host, that persistent memory will be presented back to you. So each time you're dealing with events, you have access to your memory, but you also have to update your memory effectively so that if you get re-exec'd somewhere else entirely, you still have your memory effectively. So that way, this way you can deal with an event. In other words, you don't defer the event and say, send this event back to me in a future life, right? You say, okay, I've now handled this event, but I'm going to remember something, right? And then later on, effectively, you can use that memory. So deferring an event is a kind of persistence, right? Because what you're saying is, in this lifetime, I can't deal with that event, right? Bring it back to me in a future lifetime. Maybe then I'll be able to deal with it. That's a kind of persistence. That's a kind of memory, right? But another way to do that is to say, okay, I have seen that event, I've handled that event, and I've made a note of what I need to know. Even if I couldn't fully execute effectively on what that event was doing, I have a memory now that there's something in queue, or there's something that I need to remember because that event happened. But you don't have to deliver that event back to me. I've handled that event.
So to summarize what happens underneath, each object in the framework has an identifier that allows the framework to persist that data across root executions and restore it automatically. You need to use the stored state type and have an attribute that holds this an object of stored state on your, say, charm type, and the attributes on this can be basic Python types, such as this, sets or dictionaries of strings, integers, and floats are also supported. And you can set a value that will be a default to initialize your state. So we've touched upon the concept of deferring an event, but just to go through that in a little bit more detail. you could have a handler that would look at some state variable or some other condition that is inferred from the target system and decide whether it is ready to handle that event or not. And so if you're ready, let's say if TLS is configured, then you write your config files and reload your service. But if you're not ready, but you still want to handle that event in the future, you just defer it. And that adds it to an event queue, which is then processed on the next loop execution. So all of your deferred events will be re-emitted when another event happens. So your backend relation changed event will be re-emitted when, say, a config changed event happens or some other event happens. This allows you to preserve the order of events in the distributed system and also defer certain activities until the time the right data is available. You don't always need to use this mechanism because sometimes the data is just not there and you have to wait for more data. It's not that you are not ready to process it, it's just there is no data on a particular relation for you to react to. So, but if your charm is not ready or you're waiting for some data from a different relation, then you need to defer an event and make sure you haven't forgotten the particular event that happened. So in order to help with creating your charms, we provide a representation of a model that Dmitrii gives to a unit. So your model will contain different objects that represent your application, your unit, your config dictionary, your relations and their data. There are also additional concepts that we have related to storage, providing resources associated with charms and networking. So all of that is exposed in the model object that you can access through reference to yourself. So you would use something like self.model to access those attributes. The model object also has some methods to query for objects that you need to use. So for example, if you know that there will only be one relation created for a particular endpoint, you'll be able to use the get relation method to obtain just one instance. And if there are multiple instances and the charm just doesn't support multiple relations, you will get an exception back. A similar thing is available for network bindings. That's feature in Dmitrii called network spaces and allows you to model the logical networks and work with multi-homing. If you're interested in this concept, please reach out to us. We'll be able to answer your questions, but it's a pretty advanced topic, so I won't stop on this one here. So if you want to try creating something simple, you just need to create a charm structure. There are a couple of steps here on how to create the basic one. It's just to give you an impression that there's no magic in the creation of a given charm. So you need to have a couple of directories created where your source and your modules will reside. The framework itself can be added as a submodule to Git repository, and your charm code will reside in the source charm PI. And you can structure your charm by using symlinks. So you can put your modules, your GitHub modules under mod, and then symlink them to your lib directory. And you can do the same with your charm source code and have a hook symlink created in the hooks directory. You'll need a metadata file with at least this content to deploy a charm. And this is, again, a very basic charm if you want to start. And again, your structure is, as we described it before, you have a charm declaration and the hello world charm, which is log a message using the standard logger. We've used the standard Python logging mechanism and hooked it up to use digital logs, so you don't need to chill out to use that tool. You can just use the standard Python logger with the framework. And with that, I'm going to transition to the
Okay, is there any questions regarding this last part of the presentation? Okay, so I received one question from a colleague from the University of the Basque Country, and I made some slides to explain it. Okay. Okay. So the question that that this person is asking is, if you have an HTTP server service scaled to 1 BDU, and then it's scaled out to 3 BDUs, does OSM balance the work or the load between all the workloads? So I think that to answer this question, we have to think of two cases. The first one is if we are working with VNFs or BDUs, okay, and the other approach would be with Kubernetes. So, for example, in this case, well, OSM doesn't balance the workloads. OSM is just it offers just the tooling for deploying and operating the workloads in the in different VIMs and Kubernetes and so on. Okay. So in this case, we will need a load balancer VNF, for example, and an HTTP VNF, and a relation between those in which the HTTP service will tell the IP to the load balancer. So the load balancer knows which list of servers does it have available to load the balance. Okay. So in this case, we will have one IP. Okay. I could have more details, but I didn't have time for it. But okay, so imagine that the BDUs are scaled to 3. Okay, so now we have 3 IPs. In this case, the relation will trigger some events, and this application, each one of these units will add their IPs to the relation so that the load balance is reconfigured and he knows about those 3 IPs. Okay, and the cool thing is that if we do this with Kubernetes, it's slightly different because Kubernetes already offers some features that allows him to load balance. Okay, so imagine that we have the operator container that we saw before, that is the charm. Okay, and then we have the workload containers. In this case, we have one workload container that has the IP1. Okay, but Kubernetes offers or assigns a cluster IP to this application. Okay, so basically, if you go to this cluster IP, Kubernetes will automatically balance between the different workloads. Okay, so the workflow could be something like that: the charm operator, okay, will trigger the scale event, let's say, and the workloads will scale to the number of units that the operator set. So each workload will be assigned with one IP, but anything should change here because the cluster IP, because Kubernetes will know which IPs does it have to load the balance. Okay. So I think that answers the question.